Thank you. Hello, everyone. So I'm going to talk about gradient boosting and Numba. Gradient boosting are these very fast and efficient machine learning predictors, and Numba is a just-in-time compilation library for Python. And the reason for this talk is that we've been working on PyGBM with Olivier Grisel, who's a software engineer at INRIA in Paris. And PyGBM is an implementation of gradient boosting in Python using Numba's just-in-time compilation. And we were able to reach performances that are on par with XGBoost or LightGBM, which are specialized gradient boosting libraries in C++. So this talk is going to be in 3 parts, which are pretty much independent. In the first part, I'm going to try to convince you that gradient boosting is some kind of gradient descent. So this is going to be a bit about theory a little bit. The second part is going to be about algorithms, and I'm going to explain how to go from a slow implementation of gradient boosting to a very fast one. And in the third part, I'm going to do some kind of field report from our use of Numba when we were developing PyGBM, the stuff that we liked, the stuff that we liked a little bit less. So both Olivier and I are core developers of scikit-learn, and recently we ported the code from PyGBM from Numba to Python so that it could be included in scikit-learn. So we now have very fast estimators for gradient boosting in scikit-learn, and we use Python for that. So I'm going to talk about this a little bit too. Slides are online, by the way, and you can also find them on my Twitter. So what is gradient boosting? There are many ways to explain what it is. The easiest way for me to understand it is to see it as some kind of gradient descent. So you might already know that the prediction of a gradient boosting estimator is this y hat thing is the sum of the prediction from some weak estimators, which are usually decision trees. And that wasn't obvious to me at first, but those decision trees, they don't even try to predict the target directly. They try to predict something which is very different. They try to predict gradients, and that sum that you see here is actually some kind of gradient descent. And the way I like to explain it is to make a parallel between the way that we do gradient descent for gradient boosting and the way we do gradient descent for, let's say, linear regression. So in both cases, you start with a loss function that you try to minimize. This is common to both estimators. For linear regression, this loss function is the least square loss. And for gradient boosting, you can also use the least squares loss, but you can also use pretty much any kind of loss that is differentiable. In linear regression, you have a model, so you have this parameter theta that you want to estimate. In both cases, we want to minimize the loss. The difference between the two techniques is that in linear regression, we're going to minimize the loss with respect to this parameter theta, whereas in gradient boosting, we're going to minimize the loss with respect to the prediction vector, y hat. And that might seem strange at first, but it makes sense in the sense that y hat is a parameter of the loss, just like this theta is also a parameter of the loss, and they're both vectors. They're not the same dimension, but they're still both vectors, so they're the same kind of object. So there's nothing keeping us from minimizing the loss with the training set predictions. And if we actually do that, we have that kind of gradient descent here, and you can see that this is exactly, both equations are pretty much exactly the same. The only difference is that we've replaced this theta parameter with the vector of the prediction, and both are gradient descent, and the one on the right is what we do with gradient boosting. So if you actually, so that's what I like to call hack number 1. There's going to be a second hack, but the first one is that you optimize your loss with respect to your training set prediction. And if you do that in code, you have this compute gradient function here, which is nothing but the right-hand side of the equation, the derivative. And you start with some random prediction, or you can initialize with 0. And gradient descent is this iterative process where you update the value of the prediction with this update step here when you have computed your gradient at the beginning. And really, if you do that, this is almost already gradient boosting. We're almost there. If you do that, you'll see that your loss, your training loss, is going to decrease and is going to be very close to 0 at the end. And that will mean that your training set predictions are extremely close to the target. But there's one thing that we haven't done yet, is that even though we're super performant on the training set predictions, we're not able yet to predict on new data. And here comes hack number 2, is that instead of using the exact value of the gradient in the update step, we're going to use the prediction from a weak estimator, which is going to be a decision tree, to predict those gradients. So, by the way, this piece of code here is exactly how we implemented gradient boosting in scikit-learn in the previous version. This fits in a few lines of code only. So you still compute the gradient at the beginning like we used to do, but we're going to fit a decision tree to predict those gradients now. And we're going to use the value of the predictions here instead of the exact value of the negative gradient. And by doing that, we can reuse those estimators, the weak estimators age here, we can reuse them to predict for any kind of new data. And this is this function here. We just sum over all the predictions of those estimators, and this function predict corresponds exactly to this equation that we saw before. And really that's all there is to, that's pretty much all I know about the theory of gradient boosting, and I hope you now understand that it's some kind of gradient descent. So to sum up, what we do is we choose a loss that we want it to be differentiable. Hack number 1, we optimize with respect to the prediction instead of optimizing with respect to a model parameter. Hack number 2, we use weak predictors to predict the gradients instead of using the actual value of the gradients. And then we can use those weak estimators to predict for new data. That's it. All right, so I'm now going to explain a few tricks to go from a slow implementation like the one we saw to a very fast implementation. And the tricks that I'm going to describe are the tricks that are implemented originally in LightGBM and that we also used in PyGBM and now in scikit-learn. So what is slow in gradient boosting? The slow part of gradient boosting is fitting the decision trees, right? We have to fit a decision tree at every single iteration, and that's the bottleneck. How do we fit decision trees? We start with one node, which is the root, and all of the samples are in the root originally, and we try to find the best split point, the split point being defined by a feature and a threshold to split on, and basically all of the samples whose feature value is less than these thresholds are going to go to the left node, and all the rest are going to go to the right node. So once you split your first node, you end up with 2 other nodes that you want to split again, et cetera, and you split all of your nodes until you stop until you reach some sort of stopping criterion. And the slow part of fitting this tree is finding the best split point at every single node. You have to find the best feature and the best threshold. And this is what is slow, and it looks like this. So for every single feature and every single possible threshold, you need to compute a gain of this given split point, and the gain tells you how good it would be to split with this split point. And then you choose the best split point that has the best gain, basically, at the end. One thing that we need to understand here is that this gain that we ultimately want to compute, it only depends on sum of gradients of the samples, and these gradients are exactly the same gradients that we've seen before in the theory part. The sum of the gradient at the current node, they're easy to compute, that's fine. The ones that are more tricky to compute are the sum of the gradients in the right and the left potential children. These are more tricky to compute. And the only way we can do it approximately fast is by sorting the feature values every time. So that's the bottleneck of the algorithm right now, is that this sorting step is an n log n operation. So we need to make it faster. And the way we are going to make it faster is by using those histograms data structure that ultimately are going to enable us to compute those gradients in the left and right child without having to sort the feature value. So I'm going to explain how we do this. The first trick that you need to implement is to bin your data. So you have this training data here with 4 samples and 2 features. And binning the data is a very simple process of mapping those infinite range real values to a very small integer range. We usually encode the bins over 8 bits, so you have 2, 5, 6 possible values for your bins. And a very nice feature now that we have about our data is that we can use the feature values as indices because there are small integers between 0 and 255. And that enables us to create those histograms. And a histogram is a very simple thing. It's literally just an array, And the size of the array is the number of bins. So every single bin is mapped to a cell in the array. And every single entry of the histogram contains the sum of the gradients of the samples that are mapped to that bin. So to give you an example, here I have the histogram of the second feature, and we see that the first sample is mapped to the first bin, so the first entry of the histogram is just a gradient of this sample. And if you consider the last bin, we see that the last two samples are mapped to the last bin, so this last entry in the histogram contains the sum of the gradient of these two samples. And really, that's all there is to it. And if you remember that what we ultimately want is compute the gain of every single split point, and the gain only depends on the sum of gradients, well, this is exactly what the histograms are telling us. So we bin the data once and for all before we do any kind of training process. And then during the split finding procedure, we're going to build histograms. And building the histograms is pretty easy. It's an O of n operation, where n is the number of samples. You just go through all of your samples, go look what bin they belong to, and update the value of the bin in the histogram. So that's pretty simple. So now the split finding procedure looks like this, and this is the fast version. We still go through every single feature, and at the end we still compute a gain. That part doesn't change, and we keep the base gain. What changes is in the middle, instead of sorting the feature value, we will build a histogram, which is O of n operation, and then we go through every single bin, and we compute the gain with this feature and this threshold. So the gain, like I said, the gain only depends on the sum of the gradient in the left and right child. And this is exactly what the histogram is telling us here. We go through every single bin of the histogram and look, oh, should I split here? Okay, maybe I compute the gain, and then see what gain is the best over all the histogram. So we went from something that was n log n to something that is now O of n plus O of n bins, and since the number of bins is extremely small compared to the number of samples, this is a tremendous gain of speed. So I said that the histogram building is O of n. It's actually slow. We can actually do better than this in half of the cases with this subtraction trick. The idea is that when you have a parent and two children, you know that all of the samples that are in the parent, they are either going to be mapped to the left or to the right child, right? They can't go anywhere else. So the sum of the gradient that's at the top is also going to be mapped to one of the children. And since the histograms are nothing but arrays of sum of gradients, that means that the histogram of the parent is always equal to the sum of the histogram of his children. So when you know the histogram of a parent and one of the siblings, then you can just compute the histogram of the remaining one by just subtracting the two histograms. And that's a O of n bin operation, which is even faster than the O of n operation. So in half of the cases, computing the histogram, which is currently the bottleneck of the algorithm, comes for pretty much for free. And that's pretty much all there is. So the three tricks: bin your data, compute histograms, and build a subtraction trick. That's pretty much what makes LightGBM so fast now. All right. So last part, I'm now going to talk about Numba. For those who don't know, Numba is a just-in-time compilation library. So basically, you write pure Python code, you add a few decorators here and there, manually write your for loops, and Numba magically compiles your code when you're running your script. It compiles your code to very fast machine code. So I'm going to describe a few features from Numba that we thought were really useful when we were developing PyGBM with Olivier. So this is a simple example. This function implements the subtraction trick that I've just talked about before. So it's a function that takes as input two histograms, and it allocates the output inside of the function, and then we just manually write our for loop, subtract the values of the histogram, and we return the result. That's extremely simple, and this ng decorator tells Numba to compile this piece of code. As you can see, that's very simple code. It really looks like Python. The only difference is that if I were just using pure NumPy, I would use the vectorized version of the subtraction. Here in Numba, I just have to write my for loop manually. So it's very easy to do. And by the way, I lied to you before. The histogram is not just an array of gradients. It has other fields. That's why The histogram D type here contains more than just the sum of the gradients. But Numba is able to handle it seamlessly. It works really well with pretty much any NumPy feature that we came across. So that's very, very convenient. It also has support for parallelization. So if you want to parallelize, if you want to call this function in parallel, all you need to do is use it inside of a p-range instead of a range. It has different backends, OpenMP and Intel TBB, and another one that I don't remember. So that's very easy to do. In comparison, if I were to write that in Python, and I actually did, it's a little bit more involved. Python, if you wanna use custom D types like that in Python, you need to declare the D type in Python like we did right here, but you also need to declare a C struct somewhere that's going to mimic this NumPy D type, and you're going to use this C struct in your Python code. So that's a little bit less convenient. And also, as you can see here, so this function can be called in parallel, and we are allocating this out array inside of the function. There is no way we would be able to do that in Python, because Python requires you to release the GIL every single time you're running things in parallel. So you're not allowed to have any kind of Python interaction inside of your parallel code. Numba is able to handle it somehow. I don't know how, but that's extremely convenient because you don't need to worry about that kind of things. This is another example. I'm not going to detail. This is another optimization that you can do, by the way, to speed your gradient boosting code. I'm not going to detail the logic. What's important here is to see that this function, update prediction, it runs in parallel, and it has this leaves data parameter that I described in the picture above. And this leaves data is a list of tuples, and each tuple is a combination of a float and a view, a memory view on some array that is allocated somewhere else. So it's a very Python object, you know, it's like nested list of stuff. And Numba is able to handle it perfectly. That's so convenient because this code actually looks like Python code. If I were to write this in Python, that would not look the same. Having those lists that are different length, these memory views like that, is much more trouble. So pretty much every time you have a Python object that has homogeneous types like this, Numba is able to handle it very, very well. It's actually fast, so this is a small benchmark on my laptop on the Higgs boson dataset, which is like 10 million samples, and it's pretty much a standard when it comes to evaluating gradient boosting algorithms, implementations. So PyGBM runs in about 43 seconds on my laptop, and LightGBM runs in about 42 seconds for this. So Numba really gives us a huge computation speed here. Don't take it for granted, it's just a benchmark on my laptop run one time, so it doesn't mean much, but you can still see that Numba helps a lot here. So our overall experience with Numba was really great. The things that we really like, first of all, the doc is really good and is very helpful. And that's, in my opinion, that's just such an important thing for packages like this. So congrats to and thank you for the Numba core developers to maintain such a high quality documentation. The barrier to entry is pretty low. All you need to do, like I said, is you have your Python code, write your for loops manually, add a decorator, and that's pretty much it. You're done in most cases, so that's very easy, and that lets you keep your code Pythonic too. You can still use your dictionaries, your list of tuples or whatever. That's still going to work, so that's very convenient. And it makes it very fast to go from your slow implementation to an optimized version that Numba can optimize. There are a few things that we wish would improve. First of all, the error message weren't super helpful most of the time. I assume they are more targeted towards Numba core developers rather than Numba users. Honestly, even after a few weeks of working with Numba, I still had no idea what the error message was telling me. I wish this thing would improve. In contrast, the Python error message are extremely helpful, and they really tell you exactly what you need to do, pretty much, to fix the problem. Compilation may take some time, some non-negligible amount of time. Probably not for small scripts, but for a project of the size of PyGBM, which is a few thousand lines of code, it takes about 10 seconds. So it's not just about using the package, it's also about developing the package. Like when you're writing a test, you have to wait 10 seconds until you can actually run it. You change your test, wait 10 seconds again. So that takes some time, and I wish we had some kind of caching the result for compilation so that it would just run faster. There are still a few bugs, so that one is a big one. You know, when you experience a bug, when you're developing something and you see a bug, the first thing you do is, oh, I did something wrong. And when I was working on PyGBM, 90% of the cases that was true. I was doing something wrong. But in 10% of those cases, Numba was actually doing something wrong. And it takes a lot of time to go from, you know, to make sure that your code is correct, that your tests are correct, that your mental model of something as complicated as gradient boosting is correct too, and actually find out that what is not correct is the tool that you're relying on. That can take a lot of time, and that can be a little bit frustrating too. There are a few missing features. For some reason, we cannot parallelize methods. We can parallelize functions, but not methods. We cannot parallelize over tuples, but we can parallelize over lists. So these are things that are weird from a user point of view. I assume there are very specific reasons for this, but as a user, I just find it a little bit weird. I wish we were able to control the OpenMP scheduling as well. I don't think we can tell OpenMP to use the static scheduling or dynamic scheduling right now. Profiling was a bit of an issue. It used to. I know they just released, in the new release, they did something about profiling, so that's why I kept the question mark. I'm not sure if that's still that much of an issue right now. So, and by the way, all of the points that I made here are things that Python does pretty well, usually. But so it's normal that it's not a finished product. It's still a work in progress. So having these bugs and missing feature is still a perfectly normal thing. I would definitely encourage you to try it. It's great. The more people use it, the more the Numba core developers can fix their bugs and know what user expect. Definitely use it. It's very useful. It works. It's easy to use. You can go from your pure Python code to a very fast implementation in just a few lines of code. It's very convenient. So definitely use it. There are other talks about Numba if you're interested. There's one tomorrow and there's one on Friday too. And by the way, if you're interested in gradient boosting estimators, definitely check out the new estimators that we have in scikit-learn. They're super fast now. They're in Python, they're not in Numba. And we're going to add features, new features. So we're going to add support for missing values and support for categorical features as well. And it's going to be great. Thank you very much.
So we have some time for questions.
Hi, nice talk. Numba will compile for GPUs as well. Did you experiment with that at all, or is it not appropriate for your app, or what?
Yeah, GPUs?
Yeah, GPUs.
I haven't used GPUs at all. I don't own one, and I don't have any experience with that. But I know Numba is able to support GPUs somehow. But
Yeah.
Unfortunately, I cannot tell you anything about it.
It's pretty. I mean, it's pretty easy extension of just what you've said about ordering a parallel compilation, but it might be worth looking at.
What's the name of the GBDT in scikit-learn?
I'm sorry?
In scikit-learn, what is the name of the gradient boosting tree that's implemented?
What is the, I'm sorry?
The name, the
There's
namespace.
a lot of echo.
What is the name?
What is the name of the estimator?
Yeah.
It's called Hist Gradient Boosting Classifier and Hist Gradient Boosting Regressor.
Well, I'll ask one question. how does the performance of the Python version of your stuff compare to the Numba version?
It's
out of
pretty much the
curiosity?
same. I haven't seen any. So it's hard to compare exactly because when we first started with the Numba version and then ported it to Python, and I realized that we were doing something in the first version that we didn't need to do. So by itself, the Python version is a little bit more optimized, but I didn't see some striking difference in the performances between Numba and Python, ignoring the compilation time.
Right. One more question.
Mine is probably, it was a math part, the first part of your talk. So you do the weak learners are learning the gradient. Once you've learned the things, how are you making the predictions of a label? Are you using the same trained weak
You mean
learners?
for classification?
Yeah, well, for regression. Because your trees predict, I mean, the weak learners predict the gradient, right?
Yes.
So now from there, how do you go to predicting the actual label?
So the gradients, in the case of regression, the gradients, and in the case of regression and for the least squares loss, the gradients are actually homogeneous to your prediction. So this equation here, you don't have to change anything. Things get much different in classification because the y hat that you're predicting with the gradients is actually, again, it depends on the loss, but for the cross-entropy loss, this is going to be a logs odd ratio. So you would have to convert your logs odd ratio with a sigmoid function or stuff like this. It really depends on your loss. And yeah, that's a very good point. What I described here is pretty much how you do gradient boosting for least squares loss.
All right, let's thank Nicholas again.
Thank you.